Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about the importance of IP addressing. Specifically in this video we're going to learn about the importance of IP addressing design, and then we're going to do a brief review of subnetting and public and private addressing, with the understanding that with subnetting and public and private addressing, you gained most of your knowledge in the CCDA series. So let's go ahead and begin with the importance of IP addressing design. One of the major concerns in the network design phase is ensuring that the IP addressing scheme is properly designed. A solid addressing scheme should be hierarchical, structural, and modular. These features will add value to the continually improving concept of enterprise campus design. This is also important in scaling any of the dynamic routing protocols. A solid IP addressing scheme helps routing protocols function in an optimal manner, especially RIP version 2, EIGRP, OSPF, or BGP. Facilitating summarization and the ability to summarize addresses provides several advantages for the network. Shorter access lists reduces the overhead on routers. The performance difference is actually very noticeable, especially on the older models. Faster convergence of routing protocols. Addresses can be summarized to help isolate troubled domains, and overall improvement of network stability. Address summarization is also important when there is a need to distribute addresses from one routing domain into another, as it impacts both the configuration effort and the overhead in the route processing. In addition, having a solid IP addressing scheme not only makes ACLs easier to implement and more efficient for security, policy, and QoS purposes, but also it functions and facilitates advanced routing policies and techniques such as zone-based policy firewalls, where modular components and object groupings that are based on the defined IP addressing schemes can be created. Solid IP addressing planning supports several features in an organization: route summarization, a more scalable network, a more stable network, and faster convergence. Now, if you're to understand route summarization, you need to understand subnetting. Let's go ahead and do a quick review of subnetting at this time. An IP address is a unique logical number to a network device or interface. It is 32 bits in length, and to make the number easier to read, the dotted decimal format is used. The bits are combined into 4 8-bit groups, each converted into decimal numbers. For example, as you will see here, this address is 10.128.0.1. The first octet dictates which class the IP address is in. As you see in this diagram, the beginning bits of the first octet will dictate what class the IP address is. There are 5 classes, A, B, C, D, and E, and let's go ahead and talk about each of those at this time. Class A addresses range from 0 to 127 in the first byte. Network numbers available for assignment to organizations are from 1.0.0.0 to 126.0.0.0. By default, for Class A addresses, the first byte is the network number, and then the 3 remaining bytes are the host number. Class B addresses range from 128 to 191 in the first byte. Network numbers assigned to companies or other organizations are from 128.0.0.0 to 191.255.0.0. By default, for Class B addresses, the first 2 bytes are the network number, and the remaining 2 bytes are the host number. Class C addresses range from 192 to 223 in the first byte. Network numbers assigned to companies are from 192.0.0.0 to 223.255.255.0. The format is the first 3 bytes are the network number and the last byte is the host number. Class D addresses range from 224 to 239 in the first byte. Network numbers assigned to multicast groups range from 224.0.0.1 to 239.255.255.255. Please note that these addresses do not have a host or network portion. Class E addresses range from 240 to 254 in the first byte. These addresses are reserved for experimental networks. Network 255 is reserved for the broadcast address, such as all 255s. Again, take a look at this table and you will see the summary of the IPv4 address classes. Each address class can be uniquely identified in binary by the high order bits. Now, subnetting plays an important role in IPv4 addressing, since you want to be able to break down the networks into smaller ones. As you can see here, we have a Class A IP address, and if we were to use its default subnet mask, it would be a /8. That is, the first 8 binary bits would be 1s and the rest would be 0s. But this would mean we have hundreds of thousands of IP addresses in this one subnet. Let's say we want to use this IP address on our internal network and simply assign it to one small portion of our network where there are 100 users. In that case, we would want to assign a smaller subnet, let's say a /24. So subnetting allows us to put it on a smaller network with fewer hosts. So the subnet mask is a 32-bit number in which the bits are set to 1 to identify this network portion of the address, and the 0 then identifies the host portion of the address. As you can see here, we will now set to 1 the first 24 bits, and that will mark off the subnet, which is now a /24, which means that 10.128.0/24 is a dedicated network that can host 254 hosts. The importance of IP addressing is reflected in the new requirements that demand greater consideration of IP addressing, as the following examples illustrate. The transition to voice over IP telephony and the additional subnet ranges required to support voice services. Data in voice VLANs are usually segregated, and in some scenarios, twice as many subnets may be needed when implementing telephony in the network. Layer 3 switching at the edge, replacing the Layer 2 switching with multi-layer switches. This involves more subnets needed at the enterprise edge, so the number of smaller subnets will increase. There should be as little readdressing as necessary, and making efficient use of the address space should be a priority. Sometimes Layer 3 switching moved to the edge will involve a redesign of the IP addressing hierarchy. Many organizations use technologies like Network Admission Control, 802.1x, or Microsoft NAT. These types of deployments will be dynamically assigning VLANs based on the user login or port-based authentication. In this situation, an ACL can actually manage connectivity to different servers and network resources based on the source subnet. Using NAC over a wired or wireless network will add more complexity to the IP addressing scheme. Many network topologies involve having separated VLANs, such as data, voice, and wireless networks. Using 802.1x may also involve a guest VLAN or a restricted VLAN, and authorization policies can be assigned based on VLAN membership from AAA server. Using role-based security techniques might require different sets of VPN clients, such as administrators, customers, vendors, guests, or extranets. So different groups can be implemented for different VPN client pools. This role-based access can be managed through a group password technique for each Cisco VPN client. Every group can then be assigned a VPN endpoint address from a different pool of addresses. If the pools are subnets of a summarizable block, then routing traffic back to the client can also be accomplished in a simplified fashion. Network designers should also consider that NAT and PAT can be applied on the customer edge routers. This is often a PIX firewall or on the ASA devices. NAT and PAT should not be used internally on the LAN or within the enterprise network to simplify the troubleshooting process. NAT can be used in a data center to support the out-of-band management of the VLAN, that is, devices that cannot route or cannot find a default gateway for the out-of-band management of the VLAN. So here's what you've learned. You've learned about IP addressing design, subnets, or an overview of subnets, and then a refresh of public versus private addressing. So as we move on in this chapter, in this video series, this foundational knowledge will be necessary as you continue to learn and grow in preparation for your exam. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about subnet design and summarization. Specifically, we're going to talk about not only the importance of IP summarization, but how to design for it, and then we will talk about how this works within routing protocols. Now you've already learned about IP addressing design. Let's dig deeper and understand this concept of summarization. After planning the IPv4 addressing scheme and determining the number of types of necessary addresses, a hierarchical design might be necessary. This design is useful when finding a scalable solution for a large organization, and this involves address summarization. Summarization reduces the number of routes in the routing table and involves taking a series of network prefixes and representing them as a single summary address. It also involves reducing the CPU load and the memory utilization on network devices. In addition, this technique reduces processing overhead because routers advertise a single prefix instead of many smaller ones.
Large enterprise networks can have routing tables with many route entries, and network summarization allows multiple routes to then be summarized into a single route advertisement. So it reduces the number of entries in a router's routing table, that eats up less memory, and also CPU because it reduces the number of network advertisements that need to be sent. And that can obviously increase convergence time as well. Here's a perfect example. Let's say we're looking at the routing table of a core router, and it knows about all the branch offices. And let's say there are 255 branch offices, and each are allotted a /24, and they're assigned a 192.168x.0/24 network. Now, sure, the core router has individual entries for all of these routes and knows how to reach all of them through separate interfaces or tunnels. But all these routes do not need to be passed individually throughout the network onto a neighbor through a route advertisement. They can be summarized using one summary route, 192.168.0.0/16. So as you can see, using summarization, we're saving a lot of memory and CPU by simply summarizing all of these routes into one single route.
A summarizable address is one that contains blocks with sequential numbers in one of the octets. The sequential patterns must fit a binary bit pattern. Another planning aspect of summarizable blocks involves medium or large blocks of server farms or data centers. Servers can be grouped based on their functions and on their level of mission criticality, and they can all be in different subnets. In addition, with servers that are attached to different access layer switches, it is easier to assign subnets that will provide a perfect pattern for wildcarding in the ACLs. Simple wildcard rules and efficient ACLs are desired, as complex ACLs are quite difficult to deal with, especially for new engineers who must take over an existing project. When implementing the hierarchical addressing scheme, it is important to have a good understanding of the math behind it and how route summarization works. This is an example of combining a group of Class C addresses into an aggregate address. Summarization is a way to represent several networks in a single summarized route. In real-world scenarios, a subnet calculator can be used to automatically generate the most appropriate aggregate route from a group of addresses. The goal is to take all of these networks and aggregate them into a single address that can be stored at the edge distribution submodule or at the core layer of the network. The first thing to understand when implementing a hierarchical addressing structure is the use of continuous blocks or IP addresses. In this example, the addresses 192.100.168.0 through 192.100.175.0 are used. Summarization will be based on a location where all the upmost bits are identical. Looking at the first address above, the first 8 bits equal the decimal 192. The next 8 bits equal the decimal 100. And the last 8 bits are represented by a 0. The only octet that changes is the third one. To be more specific, only the last 3 bits in that octet change when going through this address range. The summarization process requires writing the third octet in binary format and then looking for the common bits on the left side. In this example, all of the bits are identical up to the last 3 bits in the third octet. With 21 identical bits, all the addresses will be summarized to 192.168.0/21. Now, different routing protocols handle summarization in different ways. RIP version 2 has classful origins, that is, it summarizes by default, although it can act in a classless manner because it sends subnet mask information. Because of its classful origins, RIP version 2 performs automatic summarization on classful boundaries. So, anytime RIP version 2 is advertising a network across a different major network boundary, it summarizes to the classful network mask without asking for permission. This obviously can lead to big problems in the routing infrastructure for discontiguous networks. RIP version 2's automatic summarization behavior should be disabled in many situations to gain full control of network routing operations. In addition to the automatic summarization feature, RIP version 2 allows for manual route summarization to be performed at the interface level. The recommendation is to disable automatic summarization and configure manual summarization where it is necessary. EIGRP functions similar to RIP version 2 regarding summarization, as EIGRP also has classful origins because it is an enhanced version of IGRP. EIGRP automatically summarizes on classful boundaries, and just like RIP version 2, this feature can be disabled. And manual summarization can be configured on specific interfaces. The biggest issue with this behavior is that there might be discontinuous networks, and this could cause problems with any of the automatic summarization mechanisms described. As you can see in this diagram, the 172.16.10.0/24 subnet is on the left side, 172.16.12.0/24 is on the right side. These networks are divided by a different major network in the middle, and this will cause a problem due to discontinuous networks and summarization. Applying EIGRP to this scenario and automatic summarization enabled by default, it will summarize toward the middle of the topology, that is 172.16.0.0, from both sides. That will obviously cause major routing problems. OSPF does not have automatic summarization feature, but two different forms of summarization can be designed: summarization between internal areas and summarization from another separate domain. Summarizing from one area to another involves a type 3 LSA. Summarizing from another domain involves two types of LSAs in the summarization process: a type 4 LSA, which advertises the existence of the summarizing device, and the actual summary of information, which is carried in a type 5 LSA. BGP uses just a single type of summarization called aggregation. If you aggregate, in the vast majority of cases, you will be specifically typing in the command to aggregate those addresses. So here's what you've learned. You've learned about IP subnet summarization beyond just the basics. You've dug deeper, and specifically, especially with the routing protocols, understanding their behavior so that you can design accordingly. You certainly will be asked questions about this on your CCDP exam, but you will also be asked questions about this as you design for the enterprise. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to continue to learn about addressing design. Specifically, we're going to talk about IP address planning, and then we're going to talk about role-based addressing. So let's begin. An important issue in IP addressing design is how the addresses will be assigned. Obviously, one way would be to use static assignments, but the other and much more popular way is to use dynamic protocols such as Dynamic Host Configuration Protocol, or as you surely know it, DHCP. Deciding on the address allocation method requires answering some of these questions. How many end systems are there? For example, if there are a small number of hosts, less than 50, you may want to consider using static or manually assigned addresses. However, if there are several hundred systems, that's just not realistic, and you're going to use DHCP to speed up the address allocation process. The other question you would want to ask is, what does the security policy demand? Some organizations demand the use of static IP addressing for every host or for every node to create a more secure environment so that the IP addresses are not being assigned or being allocated over the network wire. For example, an outsider cannot plug into a station on the network, then automatically get an IP address, and then have access to internal resources. The organization's security policy might demand static addressing regardless of the network size. Another question you'll want to ask is, what is the likelihood of renumbering? This includes the possibility of acquisitions and mergers in the near future. If the likelihood of renumbering your IP addresses is high, then DHCP should obviously be used. The next question is, are there any high availability demands? If the organization does have high availability demands, DHCP should be used in a redundant server architecture. In addition, static addressing should always be used on certain modules in certain devices. For example, corporate servers, network management workstations, standalone servers in the access layer submodule, printers and other peripheral devices in the access layer submodule, public accessible servers in the enterprise edge, remote access layer submodule devices, and WAN submodule devices. Now, building off of this, you will want to then implement IP addressing in a logical manner. Now, the most obvious approach to implementing role-based addressing is to use the network 10 dot whatever. This has the virtue of simplicity. A simple scheme that can be used with layer 3 closets is to use 10 dot the number for the closet dot the VLAN dot whatever the last octet you'd like it to be, to avoid binary arithmetic. This approach uses the second octet for closets or layer 3 switches, the third octet for VLANs, and obviously the fourth octet for hosts. If you have more than 256 closets or layer 3 switches to identify in the second octet, you may use some bits from the beginning of the third octet, because you probably do not have 256 VLANs per switch. Another approach is to use some or all of the Class B private addressing blocks. This approach will typically involve binary arithmetic. The easiest method is to allocate bits using bit splitting. In the case you see before you, you start out with 6 bits reserved for hosts in the fourth octet, or 62 hosts per subnet, or VLAN. The X bits are to be split even further. This format initially uses decimal notation to the first octet and binary notation in the second, third, and fourth octets to minimize conversion back and forth. This addressing plan is enough to cover a reasonably large enterprise network. Another 4 bits are available to work with in the second octet if you need it. Using a role-aware or ACL-friendly addressing scheme, you can write a small number of global permit or deny statements for each role. This greatly simplifies edge ACL maintenance. It is easier to maintain one access list for all edge VLANs or interfaces than different ACLs for every layer 3 access or distribution switch. You will also want to spend some time focusing on IP addressing for VPN clients. As role-based security is deployed, there is a need for different groupings of VPN clients. These might correspond to administrators, employees, or different groups of contractors, consultants, etc. You can use different VPN groups for different VPN client pools. Role-based access can be controlled via the group password mechanism for the Cisco VPN client. Each group can be assigned a VPN endpoint addressed from a different pool. Traffic from the user PC has a VPN endpoint address as its source address. The different subnets or blocks of VPN endpoint addresses can then be used in ACLs to control access across the network to resources, as discussed earlier for NAT nodes. So here's what you've learned. You've learned about address planning, and then specifically about the importance of role-based address planning to make it easier to manage your network. Cisco deems it important to approach your address planning logically, not only so it's easier on you, but also for anybody new to your environment, that someone who is new to the environment can get to work right away and understand the network much easier with proper planning. This is important information for your architecture exam, and I'm sure you'll do well on this portion. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video we're going to be covering network address translation applications. Specifically, we're going to talk about how you're going to apply NAT, or how Cisco suggests you apply NAT on the network. So although you surely understand the basics of NAT and PAT, we're going to go a little bit deeper here and understand how this should be applied within your designs. That being said, within this video there is a quick refresh, in case you need it, of NAT and PAT as well at the very end. So although the goal with IP version 6 is to avoid the need for NAT, NAT with IPv4 will still be used for a while. NAT is one of the mechanisms used in the transition from IPv4 to v6, so it's not going away anytime soon. In addition, it is a very functional tool for working with IPv4 addressing. NAT and PAT are usually carried out on Cisco ASA devices, which have powerful tools to accomplish these tasks in many forms, including static and dynamic NAT, identity NAT, and policy NAT. A recommended best practice is to try to avoid using NAT on internal networks, except for situations in which NAT is required as a stopgap measure during mergers or migrations. NAT should not be performed between access layer and the distribution layer, or between the distribution layer and the core layer. Following this recommendation will prevent address translation between OSPF areas, for example. Organizations with a merger in progress usually use the same internal network addressing schemes, and these can be managed with NAT overlapping techniques, often referred to as bidirectional NAT. And this translates between the two organizations when they have an overlapping internal IP addressing space that uses RFC 1918 addressing. If there are internal servers or servers in the DMZ that are reached using translated addresses, it is a good practice to isolate these servers into their own address space and VLAN, possibly even using private VLANs. NAT is often used to support content load balancing servers, which usually must be isolated by implementing address translation. NAT can also be used in the data center submodule to support a management VLAN that is out of band from production traffic. It should also be implemented on devices that cannot route or cannot define a gateway for the management VLAN. This results in smaller management VLANs, not a single large management VLAN that covers the entire data center. In addition, large companies or internet entities can exchange their summary routes, and then they can translate with NAT blocks into the network. This will offer faster convergence, but the downside is an increased troubleshooting process because of the use of NAT or PAT. Now, PAT is harder to troubleshoot because one or a few IP addresses are used to represent hundreds or possibly even thousands of internal hosts, which all are using TCP and UDP ports to create logical sockets. This increases the complexity of troubleshooting because it is difficult to know what IP address is assigned to a particular host. Each host uses a shared IP address and port number. If the organization is connected to several different partners or vendors, each partner can be represented by a different NAT block, which can be translated in the organization. Now that we've talked about design considerations, let's go ahead and do a quick refresh of NAT and PAT, because any of this is fair game on your exam. The first thing you need to understand when we talk about NAT are the different types of NAT IP addresses. So I created this simple chart for you, which hopefully will help you memorize each of these address types. Now, when I referred to inside or outside, inside is inside a network, and outside would be outside of your network, such as the internet. So inside local is a private IP address. And when I say private, I mean RFC 1918. So it's a private IP address referencing an inside device. Inside global is a public IP address referencing an inside device. Outside local is a private IP address referencing an outside device. And then outside global, a public IP address referencing an outside device. As a memory aid, just remember that inside always refers to an inside device. Outside always refers to an outside device. When you see the word local, think of that as private. That is private IP address that is not routable on the internet. And global, that should remind you of the internet, because global addresses are IP addresses that are routable on the internet. Now, an inside local address can be randomly assigned an inside global address from a pool of available addresses, or it can be specifically assigned an address from a static configuration. Now, whatever you choose will determine what type of NAT or network address translation you're using. There are two approaches to NAT. The first is dynamic NAT. Now, dynamic NAT occurs when an inside local address or addresses are automatically assigned to an inside global address from a pool of available addresses. And then there is static NAT or SNAT. And you might want to statically configure the inside global address assigned to a specific device inside your network. So, an example of that might be, let's say you have an email server that is inside of your company, and you want other email servers on the internet to send email messages to your server. But they need to point to a specific IP address, not one that's randomly selected. So in this case, you would choose SNAT or static NAT and specifically assign a global IP address to represent that mail server. Next is port address translation. And PAT addresses a limitation of NAT. And the problem with NAT, well, it's not really a problem, it's just a limitation, is that it does have a one-to-one mapping of inside local addresses to inside global addresses. But, what if you're in a situation where you only have one IP address to use? One IP address assigned to your firewall, one public IP address, but you have 100 users that need to get out to the internet. They can't each wait to use that IP address. So what PAT does, it allows multiple inside local addresses, your private IP addresses, to share that single inside global address. And it uses port numbers to keep track of separate communication flows. So here's what you've learned. You've learned about network address translation applications in the enterprise. That is beyond just the basics of NAT, but how specifically do you design for it. And then you received a quick refresh on the most common components of NAT and PAT. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about designing IPv6 addressing. First, you're going to learn about IPv6 addressing, but then specifically we're going to talk about how this addressing can be assigned on the network. There are many different options, not only in how you deploy IPv6, but actually ongoing how IPv6 is managed and rolled out. You need to understand both to do well on your exam, but also to master IPv6 on the network. So let's begin.
So let's ask the basic question, why even upgrade to IP version 6 other than the fact that you simply get more IP addresses? Well, there's a lot of reasons why you would want to upgrade to IP version 6, and here are a few of them spelled out for you, which I think you'll need to know for your CCNP route exam. But please note, you no longer need NAT or PAT. It has inherent IPsec support. These are key and critical updates. Now, once you've committed to using IP version 6, you need to understand how these different IP addresses are labeled. There's a global unicast address. These are unicast packets sent through the public internet, like public IP addresses. Unique local, which are unicast packets inside one organization, which is basically equal to your private IP addressing. Link local, which are packets sent to a local subnet and are not routable across networks. And then finally, take note of the loopback address, which you know from IP version 4 is 127.0.0.1. IP version 6 also has a loopback addressing as well. An IP version 6 address has 128 bits broken out into 32 hexadecimal numbers organized into 8 quartets. So here is the hexadecimal numbering system, which I'm sure we won't need much of a refresher on, but we do need to use it to understand IP version 6. And here is an IPv6 IP address. And as you can see, it looks quite long, mainly because we're used to looking at IP version 4 addresses. So this ups the game a little bit, and we may begin to wonder how we're going to support this on our network or document this, and we get concerned about managing a network with addressing this long. Well, there are built-in mechanisms within IP version 6 to help us manage it, and we're going to cover that. There's ways you can summarize IP version 6 addresses to make it more manageable, not only to read, but to understand and explain to other people. So you can shorten an IP version 6 by omitting the leading zeros in any given quartet, or you can represent one or more consecutive quartets with a double colon. So here you see an IP version 6 address with many zeros in it. Here's how we can summarize it. On the left-hand side, you can see that we used a double colon to represent the first, the second, and third quartet, and then we summarize the remaining quartets of zeros. And in the second example, we did the opposite. We summarized the first 2 quartets with zeros and then used a double colon for the end. You can only use the double colon once in an IP version 6 IP address. So here we see an IP version 6 IP address, and this is the subnet. Remember, it's a /64, so we're matching the first 64 bits, as you see here. And this also can be summarized. You don't need to write out all these zeros. So to explain what the subnet is to somebody, you can simply write it out this way. So IP version 6 is manageable. It gives you tools to manage it. So whether you are reviewing documentation or holding a general discussion about your network, or simply logging into a Cisco router to take a look at what's going on, understanding abbreviation is key to IP version 6. Here are some other ways we can understand IP version 6 addressing. In our first example, you'll see that it's 2000 and then a double colon /4. The /4 would match the first 4 bits. In hex, that would be 0010. So all addresses whose first 4 bits are equal to the first 4 bits of the hex number 2000. In the second example, we're matching all addresses whose first 20 bits match the listed hex number, and you can see in red what match that would be. And in the final example, all addresses whose first 32 bits match the listed hex number. Here's another IP version 6 address. How do we break it out into subnets? Well, here you have it. We're honoring the first 48 bits of this range, and then we are breaking this out into smaller subnets, as you can see here. Each subnet matching the first 112 bits.
So let's continue. Next, let's talk about IPv6 global unicast address assignments. So IPv6 actually has 4 major options for IPv6 Global Unicast address assignment. And you need to be aware of all four, so let's cover those. This chart's been created for you to understand these four options a bit better to help you study. You have stateful DHCP, stateless auto-config, static configuration, and then static configuration using EUI64. Now, I'm not going to go through every detail here. I just want to point out some things that are important to note. Now, if you'll remember, in IPv6, the clients are receiving the following information: prefix and length, the host address, the default router, and the DNS servers. And this can vary depending upon which method you're using. You need to understand which method or how these items are learned depending upon the method. Now, one acronym you see frequently in this chart is NDP, and we're going to go into NDP shortly. You certainly will need to know that. But also in this video, we're going to go into stateless versus stateful configuration. So you'll see the words stateful DHCP, stateless autoconfig under the DNS server assignment. DNS servers are known via stateless DHCP. So we are going to be digging into that as well, so you understand stateful and stateless concepts. But I just wanted to point these items out for you. As you learn more about this, feel free to come back to this chart to study it for your exam. We need to revisit these words stateful and stateless so that you can understand what exactly that means. IPv6 hosts can use stateful DHCP to learn and lease an IP address and the prefix length, the mask, and the DNS IP address. Now, since you have a baseline knowledge of DHCP for version 4, it'll help to compare and contrast IPv4 and v6 DHCP services. With IPv4, the host sends a multicast packet searching for the DHCP server. And when a server replies, the DHCP client sends a message asking for a lease of an IP address. And the server does reply. And the same is true for IPv6. But the server obviously provides an IPv6 address instead of v4. And then it also provides prefix length DNS IP address. And please note that stateful DHCP version 6 does not supply the default router information. Instead, it relies on NDP, Neighbor Discovery Protocol, between the client and local routers. DHCP version 4 servers retain state information about each and every client, such as IP address leased to that client, and the length of time for which the lease is valid. So version 4 tracks the current state of DHCP clients, where version 6 DHCP servers do as well, but please note they have two operational modes. First is stateful, in which the server tracks state information, and then there's stateless, in which the server does not track any state information. We'll cover stateless in a minute. Now, one big difference between version 4 and version 6 DHCP operations is that version 4 hosts send broadcasts, and version 6 hosts send multicasts. So IPv6 multicast addresses have a prefix beginning as you see here. The first 8 bits of an address are all ones. So routers know to forward these packets to the appropriate DHCP server. Now let's go to stateless auto configuration. The second of two options for dynamic IPv6 address assignment is stateless auto configuration, which allows a host to automatically learn the key pieces of addressing information such as prefix, host, and prefix length, plus the default router IP address and DNS IP address by using the following steps. First, IP version 6 NDP, Neighbor Discovery Protocol, particularly the router solicitation and advertisement messages. And it does this using NDP to learn the prefix, prefix length, and the default router. Next,
there will require some math, but it will derive the interface ID portion of the IPv6 using a format called EUI64, which we will cover later in this video. And then finally, stateless DHCP to learn the DNS IPv6 address. So this section examines all three topics in order. First, learning the prefix length and default router with NDP router advertisements. NDP allows IPv6 hosts to multicast a message, and it asks all routers on the link to announce two key pieces of information. First, the IPv6 address of routers willing to act as a default gateway, and then all known IPv6 prefixes on the link. So it uses ICMP version 6 messages called RS, or router solicitation, and RA, router advertisement. Now, for this process to work, before a host sends an RS message, a router connected to that same LAN must already be configured for IPv6 and must have an IPv6 address configured. So at that point, the router only knows it can be useful as a default gateway, and it knows at least one prefix that can be useful to any clients on the LAN, if and only if it has a route. If it has no routes, then it knows it can't be of any use. Now, let's talk about calculating the interface ID using EUI64. It's important to note that the value of the interface ID portion of a global unicast address can be set to any value if there's no other host on the same subnet. To automatically guarantee there is a unique interface ID, IPv6 defines a method to calculate the 64-bit interface ID. So let's go ahead and take a look at two examples. The following two lines list a host's MAC address and the EUI64 format interface ID. And now this assumes the use of an address configuration option that uses that EUI64 format. And you can see here where the MAC address gets split and then there's an insertion made, as we were just talking about earlier. Finally, let's talk about finding DNS IP addresses using stateless DHCP. Now, as you know, IPv4 servers keep a record of the leased IP addresses and when the lease expires. The IPv6 stateful DHCP server does that as well. However, for v6, the server's name includes the word stateful. So this is to contrast it with stateless DHCP server function in version 6. The stateless DHCP server function in version 6 solves one particular problem. It supplies the DNS server's IPv6 addresses to clients. So all hosts, since they typically use the same small number of DNS servers, the stateless DHCP server does not necessarily need to keep track of any state information. An engineer can configure the stateless DHCP server to know the IPv6 address of the DNS servers. And then the server tells only any host or any other device that asks, and it keeps no record of that process.
So here's what you've learned. You've learned about IPv6 addressing, but specifically how this addressing can be assigned in the enterprise. This is critical information, not just for your exam, but also as you increase in knowledge as an engineer. Good luck in your studies. Hi, this is David Voss, CCIE 11372, and in this video you're going to learn about transitioning to IPv6. Specifically, you're going to learn how IPv4 and v6 can coexist so that you can make the transition seamlessly and without downtime. We'll talk about methods you would use, such as dual stack, tunneling, and translation. So let's go ahead and begin. With the exhaustion of the IPv4 addressing space quickly approaching, it's become a high priority for organizations to begin their own deployments of IPv6. This can be accomplished in a number of different ways. The common methods include side-by-side implementations of IPv4 and v6, the implementations of tunneling over existing IPv4 networks, and the implementation of a translation process from IPv4 to v6. This video will examine these specific methods and how they can be used to support an IPv6 deployment. Let's talk about IPv4 and v6 coexistence. The transition from v4 to v6 will not be something that is done overnight. It will take a number of years before v6 has anywhere near 100% implementation. In these intervening years, a number of mechanisms have been and will be developed to make the transition as easy as possible. The first of the available options is referred to as dual stack. When using this method, an organization essentially does not transition to IPv6, but simply builds a parallel IPv6 network next to their existing IPv4 network. The second of the available options is tunneling. The basic idea behind tunneling methods is that IPv6 will be tunneled over an existing IPv4 network, and a number of different tunneling methods are available and can be selected based on the requirements of the situation. And then the third available option is translation. The idea behind translation is that a boundary router between IPv4 and v6 network is performing a translation process, and it maps IPv4 to v6 addresses and vice versa. Let's dig a little deeper with dual stack. When a network is configured as a dual stack, each device on the network is configured with both a IPv4 address and an IPv6 address. The idea being that once all the devices have implemented IPv6, the IPv4 part of the network will be depreciated. This method is common for businesses looking to slowly convert their existing devices from v4 to v6. These companies can configure their routing infrastructure to support both v4 and v6, but bring their own network devices over to v6 at their own pace. It's also possible for individual devices to be configured as dual stack and use one of the tunneling technologies discussed here. The concept behind tunneling is certainly not new. Many people use tunneling daily, but use it for other reasons. For example, many companies use IPsec or SSL tunnels to secure information. Many different tunneling methods are available for your conversion from v4 to v6. Which one to use will depend on the specific implementation, and you can use this table to help you remember why you would want to use a specific type of tunneling. The manual tunneling is used to provide a point-to-point IPv6 link over an existing v4 network, and it only supports IPv6 traffic. GRE is used to provide a point-to-point v6 link over an existing IPv4 network, and it supports multiple protocols including IPv6. 6-to-4 is used to provide a point-to-multipoint IPv6 link over an existing IPv4 network. Sites must use IPv6 addresses from the 2002/16 range. 6RD is used to provide a point-to-multipoint IPv6 link over an existing IPv4 network, and sites can use IPv6 addresses from any range. And then ISOTAP is used to provide a point-to-multipoint IPv6 links over an existing IPv4 network, and it's designed to be used between devices inside the same site. Next, let's talk about translation. The concept of address translation is not a new concept to most network engineers, but this is because NAT is implemented between different IPv4 networks in almost every residential household. The concept behind this type of NAT and the newer technologies that support address translation between v4 and v6 networks is similar. IPv6 translation technologies differ from IPv6 tunneling technologies, this is because the translation technologies enable IPv4 only devices to speak to IPv6 only devices, which is not possible with any of the other tunneling methods. However, IPv4 and v6 translation and IPv4 only translation entail a certain amount of complexity. What happens when an IPv6 only device is attempting to communicate with a device on the public IPv4 internet and only an IPv4 DNS record exists? In these situations, a second technology is required to step in and provide additional services for the connection to work. The first method to be introduced to provide IPv6 translation service was NAT, Protocol Translation, or NAT/PT. NAT-PT defined a mechanism to not only translate between IPv4 to v6 addresses, but also a built-in ability to provide protocol translation services for ICMP, FTP, and DNS. The component that was responsible for these translation services is called the Application Layer Gateway. The ALG piece of NAT-PT method raised a number of issues. With additional testing and real-life experience, a new method was introduced that separated the address translation functionality and the application layer translation functionalities, NAT64 and DNS64. DNS64 can synthesize IPv6 address resource records from IPv4 resource records. It does this by encoding the returned IPv4 address into an IPv6 address format. The selection of an IPv6 translation mechanism depends greatly on the current status of an organization's network and how fast they want to transition their devices from IPv4 to v6. Logic seems to say that those organizations with bleeding edge technologies and small staffs will probably be or are already the first people in line to transition to v6. But larger companies that have tens of thousands of network devices will most likely transition a piece at a time following the experience level of each department. The transition to IPv6 is coming, so it's good that you're learning it while you're studying for your architecture exam. You have learned about IPv4 and v6 coexistence and how to handle migrations at a higher level, learning about dual stack, tunneling, and or translation to make it happen. Now you will be asked general questions about IPv6 transitions, and certainly what you've learned in this video will be very helpful in your exam. Good luck in your studies.